Hello and welcome to this installment of Physics in a Flash. Today we're going to be talking about average speed formula number one. Ultimately, we might start out by asking the question, what is average speed? Some things to note, there are two formulas for average speed, and those are located right here. And this is average speed formula number one. On the other token, the second one is the average speed formula number two, which will be the next lesson. So we're looking at this formula here, average speed number one. Let's break down the anatomy of this formula. We can see we've got V, which stands for velocity or speed. In this case, we're talking about speed. And as you probably already know, this bar over the top of any quantity means its average. The D in this case stands for distance. In this case, the total distance. And the T stands for the total time. Now, what total means depends on the situation at hand and our needs. And this will become clearer as we proceed through and do an example. So this is our formula, average speed number one. And let me add a couple things to remember about this. One, this can be used in every kinematic situation. It may not give us an answer that we need or that we're looking for, but it can be used. It can be applied in any and every situation. And two, this one is not so well known. It is perhaps the single most important kinematics formula to know and use. It can be used to solve a much wider range of problems than is typically it's given credit for. So let's look at this a little more closely. The first thing we want to look at is this formula in terms of dimensional analysis. Now, there's two things we can do with dimensional analysis throughout this course. One of those is to just analyze formula units. And the second thing is you've probably become accustomed to doing in chemistry is you can solve problems. Like this one I've listed here at the right. What is 10 miles per hour in meters per second? But we'll do that in a moment, but I'd like to start out with the first one. Let's analyze the formula in terms of units. One of the things in physics is there's a lot of different units, and frequently students will ask, what are the units of this? What are the units of that? Well, the answer is always very easy. Find the formula for that thing and put the units into that formula. It will tell you. So here we have average speed is distance over time. Distance in physics is measured in meters, and the time is in seconds. So the units of velocity are meters per second. And whenever you see letters like this written in brackets, it usually means that it's the units. Right? So velocity or speed are measured in meters per second. So now let's get at this particular problem in terms of dimensional analysis. What is 10 miles per hour in meters per second? So we are pretty good at knowing what 10 miles per hour is because we grew up in America, but knowing what meters per second is may not be so easy. It doesn't come firsthand to us. So on the one hand, we might say 10 miles per hour. Let's see, that means that it's about 6 minutes in 1 mile. 6-minute mile might make sense to someone who runs cross country or track and field because they run about that speed, 6 miles per hour. So that gives them a reference frame. So we can know what that is in terms of what it feels like. But what does it mean in terms of a number in meters per second? Well, let's start out with 10 miles per hour. And we know we want to end up in meters per second. So we're going to perform a number of operations to get to meters per second. We have to convert miles to meters and hours to seconds somehow. Now, in physics, there are a number of conversion factors that you should just know. And one of those is 2.54 centimeters per 1 inch. That can also be written as 1 inch per 2.54 centimeters. It can also be written in words as 1 inch equals 2.54 centimeters. They're all equivalent. They basically mean 1. 2.454 centimeters is the same thing as 1 inch. So when divided, they equal 1. They a unity. They represent the same thing. So let's deal with the miles first, and we could have done the hours first as well. To get rid of miles, we need miles in the denominator, and to miles we'll go to feet. 1 mile is 5,280 feet. Now, I like to keep this simple, and when I have the 2 units and I'm writing a conversion factor, I always assign the larger unit a 1, and the smaller unit then will always be numbers greater than 1. There's always going to be more of the little things than the smaller things. We never have to deal with negative exponents and decimals in this situation. We're only dealing with numbers. So always make the larger number a 1. So that being said, we've now crossed out miles, and now we would be expressing this in feet per hour. So we want to get rid of feet, and we'll go to inches, feet in the denominator, inches in the numerator, 1 foot, 12 inches, feet are gone. And now we have inches per hour. And of course, we must get to centimeters. So getting rid of centimeters, inches on the bottom, centimeters on top, 1 inch, 2.54 centimeters. And now inches are gone, and going to centimeters. We now have centimeters per hour, and we must end up in meters. So we have centimeters on the bottom, meters on the top. 1 meter is 100, or 10 to the second centimeters. So now we have units in meters per hour. Getting to seconds now, to get rid of hour must be on top. We have minutes. 1 hour is 60 minutes. And then we have the hours canceling out. And to get rid of the minutes and go to seconds, we have minutes on the top and seconds on the bottom. 1 minute, 60 seconds. So you can see now we have meters and seconds. Now, what I recommend doing at this point, since we've done the dimensional analysis in terms of the units, is to pull the numbers out to make it easier. And when we rewrite the numbers, I recommend you write the numbers in a scientific notation form. And you'll see why. So we'll start out with a numerator, 10 times 5,280. That is 5.28 times 1,000, or 10 to the third. Next we have 12, which is 1.2 times 10 to the 1. And 2.54 is its own number. And that takes care of the numerator. Now in the denominator, we have 100, 10 squared. 60, which is 6 times 10. And 60 again, another 6 times 10. So now you can see there it's possible for us to cancel out. So we get rid of the 10 here in this case. 10 squared and 10 is 10 to the third. So those come out like so. And then I'll rewrite again so I don't make a mistake. 10 times 5.28 times 1.2 times 2.54. And all of that is going to be over 36. 6 times 6 is 36, or 3.6 times 10. Well, you notice another one appeared to cancel, the 10s, like so. Looking at the rest of them, I can see that 1.2 and 3.6 is really 1 to 3. So now rewriting again, I'm left with 5.28 times 2.54 all over 3. Wow, that's reducing quite nicely. Now, the next thing I'd like to do before I ever punch numbers into a calculator is to estimate what the answer should be in my head. So that way I know kind of what I'm looking for in case I've made a mistake. When the number pops up on the calculator screen, do you have an idea whether or not it's correct? You should have an answer in your head so that when you see it, you know it's incorrect. So I'm going to do something called an estimate. This number 5.28, I'm going to say is close to 5. I'm going to say is close to 5. And 2.54 is 2.5. Well, and I'm going to say this is about equal, 5 times 2.5. 5 times 2 is 10, and 5 times 0.5 is 2.5, so we have 12.5 over 3. Well, you can see then that 12 can be divided by 3 4 times nicely, and so we're looking at an answer about 4 or a little higher. And then when I do my mathematics in the calculator, I get 4.704, or 4.4704, excuse me, 4.4704. And the units on that are meters per second, but that's 4.4 meters per second per 10 miles per hour. Now that 4.407, if we round it up, could be a 4.5 or a 5, or if we round it down, it could be a 4. So in other words, every 10 miles per hour is between 4 and 5 meters per second. So how fast is 10 miles per hour per meter per second? Well, it's between 4 and 5. If you're driving down the road, your speedometer will say 10 miles per hour, but you're going between 4 and 5 meters per second. Interestingly enough, then, if we're going 20 miles per hour, then that is between 8 and 10 meters per second. And 50 would be times 5 is 20, between 20 and 25 meters per second. So we have a quick way now to go in our heads by knowing this conversion. We can very quickly go to meters per second. So the two things we want to remember are 2.54 centimeters per inch and 4 to 5 meters per second per 10 miles per hour, so that we can estimate properly. Now, another example we could use here is if we're traveling by air in a Boeing 747, how fast is 600 miles per hour in meters per second? Well, let's see. We have 600 miles per hour, and we have a conversion factor of 4.5, or 4, we could say 4.5, or we could say 4 or 5. On the low end, it's going to be 4. So 4 meters per second per 10 miles per hour. If you notice, these miles per hour cancel, and so we're left with 60 times 4, or 240 meters per second, or if we had used 5, we would end up with 300 meters per second. So somewhere between 240 and 300 meters per second is how fast an airplane's flying. Now that's interesting to me because I know the speed of sound is about 330 meters per second. So it's good to know those reference frames. And that's how we would use apply the tools of dimensional analysis to this formula, and how we can convert back and forth between the English and the metric system. The next thing I'd like us to do is to practice our algebra a little bit. One of the things about physics is that physics is not, many people feel that the math is hard. And it turns out the math isn't hard at all. Almost all the math is math you already know. What's difficult is applying and using math in new situations. That's what's unique about physics. But it's oftentimes very much based on your comfort with algebra. And so if you don't feel like you have a good a foundation for algebra, you might tell yourself, in physics, this is a wonderful opportunity for me to practice and further develop my algebra. Rather than it being algebra is difficult, it's an opportunity for me to develop my algebra skills. And so I will, throughout this course, I'll be working with and being deliberate about that. So we have our formula that you should know. Average speed is total distance over total time. What it means to rearrange is we want to have expressions for d equals and t equals. So to do that, we need to rearrange this formula. Now, you may have been taught that to recognize this as a series of two fractions, and in solving for d, you would first cross multiply. I won't use that language because it's not really a mathematical process. It's what it looks like. The thing I want us to remember is that if you do the same thing to both sides of an equation, it still remains equal. So in other words, if I multiply this side by 5 and this side by 5, it is true they're both equal to each other. It is true they're both equal to each other. So what I'm going to do, because I want d by itself, I need to get rid of this t. So I'm going to multiply both sides by t, and so I get tv equals dt over t. And of course, then you see these t's cancel, and I'm left with d equals vt, the average speed times the time. Now, if you notice the result of this was you cross multiplied. But fundamentally, the process is you're multiplying both sides by the same thing. So now we have this expression, and I'll rewrite it. D equals Vt, and I want an expression for t. So to do that, I need to do the same thing to both sides. I can divide both sides by v. And that gives us t equals d over v. If we apply dimensional analysis to these two, we've got average speed, which is meters per second, time, which is seconds, the seconds cancel, and the units of distance are meters. That's what we expect. Time should have units of seconds. Well, distance is measured in meters, and speed is measured in meters per second. So that is meters times seconds over meters. Meters cancel, and lo and behold, we're left with time equals seconds. So if you ever want to know the units, you can find out the units of the equation value by plugging in. You can also show that the formula works by using the correct units. So we started out by wanting to have multiple versions of the formula. This is our starting formula, and these are the rearrangements. I don't feel there's any need to memorize these others. If you have this and you know how to do algebra, you could come up with the others. The next thing I'd like to do is to do a problem. A problem where we would apply this formula to show you how it can work, even in the strangest of situations. But first, let me remind you, we are studying one-dimensional motion. And one-dimensional motion happens on a line. Now, very often for students, they see the word line, and they think it means straight line. There are all kinds of lines. There are straight lines, and there are curved lines. We might say they are curvilinear. But by just seeing the word a line does not mean it is straight. We call train routes train lines, the Hudson Line, the Harlem Line, the New Haven Line. A train track itself may be very crooked. It would have turns side to side, and it goes up and down. So it is in no shape or form straight. But from the perspective of the person on the train, it is a straight line. And it can be treated like a line, straight line. And if it's easier for you to think about, you could think about straightening out the train track in your mind. But no matter how you view it, it is a line, straight, curved, or otherwise. So that's the first thing I want us to point out, is the meaning of line in physics, and for us to think more broadly about it. The second thing is, one of the problems, since this is our first word problem in physics, one of the difficulties or challenges students oftentimes have in physics is simply making sense of what's being asked of them. They may know what the formulas are and how to plug into them, but they cannot make sense of the problem itself. So for that reason, I would like us, and I will always require you to use visual thinking routines built on visual tools. And of course, those things help us visualize what's going on. So let's start out here. We have Matt taking this path. Well, from Matt's perspective, he's taking a path, and it's a line. So we're going to represent it as a line with a starting point and an end point. I'm going to use this to help me figure out the motion and also label all the important information I have and what is missing. So in a kinematics problem that we're dealing with, we need to worry about distance, displacement, and position, and we need to worry about speed and time, at least at this level. So we have Matt starting, and we'll have him start here, and he walked for 10 hours. All right, so I'm going to put time down below. 10 hours. And he ended up at Newark Airport. The distance he traveled was 50 miles. 50 miles. Now you might be noticing we're missing the speed in this case. So we could actually figure out the average speed. V equals D over T. 50 over 10 is 5. Oh, so we've got a speed of 5 miles per hour. That's great. Well, the next thing we see is that he waited at the Newark Airport for 2 hours. He had 2 hours to spare, so he had 2 hours. And he waited there. He waited there for those 2 hours. So that means that the distance he covered was 0. So 2 hours, we have 0 miles. And if you travel 0 miles in 2 hours, well, your speed is also 0 miles per hour. So we have 0 miles per hour. And then he gets on a plane and he flies at 650 miles per hour for 4 hours and lands in LA. So we have 4 hours. And we know it's 650 miles. So in understanding this, I have these three, I have these three, and I'm missing the speed. I wrote that in the wrong place. Missing the speed. 650 miles. No, I did that wrong again. 650 miles per hour. .650 miles per hour. And so we don't know the distance. So this helps us see what information we have and what's missing. And notice everything I've solved in this case, I've used the average speed formula. Well, in this case, I want the distance. In the previous page, I derived a formula for that. And we had distance equals the average speed times the time. So that is simply 650 times 4. And 600 times 4 plus 50 times 4 is 2,400, plus 200 is 2,600 miles. So there we go, 2,600 miles. So we said in the beginning that the average speed is total distance over total time. So we can use that formula for this first segment of the journey. We can use it for the second segment of the journey, and we can use it for the third segment of the journey. What does total mean? It depends. It depends on what we're looking for. In this case, in each of these cases, it was for a specific part of the trip, but it can be used for the entire trip, in which case the average speed is total distance over total time. And our distance is now, in this case, it's very easy for me to find, 50 plus 0 plus 2,600, all over the total time, which was 10 plus 2 plus 4. So that gives us 2,650 over 16. You take a moment to figure that out on your calculators. Turns out to be 165.625 miles per hour. And what is that? That is the average speed. That's the average speed. Now, we're not worried about significant digits at this point because we're just interpreting it. 165.625 miles per hour. So let's go back and ask ourselves, what does this mean concretely? In the first segment, did he ever travel 165 miles per hour? The answer is no. It was 5 the whole time. When he was at the airport, no. During his flight, did he? The answer is yes. When they were taxiing down the runway and started to take off, there was a moment, an instant in time where it was 165, and then they continued to speed up. And on their way, on their descent and landing, they again were 165.625 miles per hour. So there were only 2 instants in time that comprised less than 1 second that this airplane was traveling at 165.625 miles per hour. So in a sense, this 165.625 miles per hour doesn't at all represent the speeds involved. 650, 0, and 5. But what it does represent, the true meaning of it is the speed at which, I mean, change that, the constant speed at which the same distance would be covered in the same amount of time. Well, that's pretty profound. In a sense, it's a substitute. We can substitute what really happened with this. A constant speed of this would get you there. One other observation I would make that we should take note is we can think about other quantities here. We can think about namely the acceleration. And it turns out in all situations we want to ask ourselves what's going on with the acceleration. And at the most basic level, before we even really learn formally about acceleration, is the acceleration constant or does it change? Well, if we think about the first part of the journey, there's no acceleration, except maybe at the very, very end, at the very, very beginning. So the acceleration is 0. And then, after we come to a stop at Newark, again, the acceleration is 0. And except for the beginning and very end here, the acceleration is also 0. But it's changing nonetheless. It changes. And the change is not steady or even. And that's all I want to draw your attention to. So in this situation, we used average speed formula number 1, and we were able to find out a reasonable answer to this, a reasonable solution to this, and interpret what it means for us. But I'll do one other thing. I'd like to do a check. We said this is the case. Let's do a check. The check should be if we traveled at that speed for that amount of time, we should cover the same distance. Is it true? Well, 165.625 times 16 does in fact equal 2,650 miles. Check. And thank you for watching this installment of Physics in a Flash.